So one big announcement, the slides for both parts of Professor Vardy's talk have been uploaded on Piazza. And now,
all right, so welcome everyone from the break, and let's continue. So just a very quick reminder of where we are in this presentation. So what we have shown is that, we can take any existing K-server PIR protocol, it's linear, and they're all linear, and then we need this sort of secret sauce, the special thing that makes it happen, which is a special binary linear code that we defined in the previous part. And then with this, we can construct a coded PIR scheme, and the storage overhead of that scheme is M over S, where what are these numbers in terms of the code? S is going to be the dimension of the binary linear code. M is the length. That's the number of servers. That's the number of columns in the matrix. That is the length of the code. Okay. So now, as far as the questions that we sort of made our goal to answer, we have understood the example. We understood the communication complexity basically remains the same, a small multiplicative factor. But what we would really want to focus about in the second part of the talk is this key question, something I promised to do, that we can reduce the storage overhead of private information retrieval to essentially 1. And we'll do that by trying to understand for which parameters M, S, and K we can construct such K-server PIR schemes. Okay, so in fact, maybe this is what I want to say on the slide. So what we have done in the first part of the talk, we started with a problem in private information retrieval, and we have been able to reduce it. Now, the only thing that is missing now is these K-server PIR codes. So you see in the previous slide, give me such a code that was the theorem, I can then use it along with any existing protocol to get a scheme. So we have really reduced our original problem to a problem in coding theory. All that remains is to come up with such codes, right? And that's what the second part of the talk will be about. And so let me introduce some notation, okay? So I'm going to use these two, capital M of S and K. What is that? So you give me K, that's the parameter. That's the K-server PIR particle that we're inviting. That's the number of disjoint columns. You also give me S, that's the dimension, that's the number of parts. And I want to know what is the shortest possible linear code I can get that has that K and that S. And I will call it capital M. And then rho is the redundancy of codes. So again, linear codes, binary linear codes, basic coding theory. What is a redundancy? It is just the length minus the dimension. Okay, so rho is M minus S. Okay. All right, so then what is the storage in terms of these two? What is the storage overhead? Well, it used to be lowercase m over S, so now the best possible storage overhead that I could get with this approach can be expressed like that, because that is the smallest m I could possibly get. Or, because this is just S plus this, it could be also written like that. Okay? So these are the two parameters that I will study in the rest of the talk. And again, a reminder of the definition. So what is the defining property of these codes? That is the property. So you give me any unit vector. I want to find k disjoint sets of columns, that's the parameter k, in this matrix, such that the sum of the columns in every set is E sub I, and that has to be true for every I such k disjoint sets must exist. And then this is what I call k survey AIR. Okay? All right, so, and why that is, maybe we've seen that on the previous slide. So again, a reminder, because we'll use it, this property is equivalent to the fact that, all right, so now you take some vector x, you encode it using a generator matrix with this property, then for every bit of the message, there are k disjoint recovery sets. So you could take some set of coordinates of the code word, add them up, and you recover the ith bit of the message. And there are k of these, and they're all disjoint. The property that we have defined on the previous slide is equivalent to that, and this is the proof that we have seen in Python. All right, so this is the problem. So this is now, we can sort of forget now about private information retrieval. This was our original motivation, but we have reduced it to coding theory, okay? And what I'd like to tell you is, so this coding theory problem is very, very easy when k is 2. Okay? K was the number of servers in the original protocol. That's our parameter. So 2 is the smallest value. And then the problem becomes trivial. Okay? So here are the values of m and rho for the special case when k is 2. And all I need to do is to add one more bit. Okay, so m of s2 is just s plus 1, and rho, therefore, is 1. And how does it work? So what is the code? So there, grayed out. So what is the binary linear code I would use to achieve this solution? What is the simplest binary linear code of redundancy 1? So you add one more bit of redundancy, that's all you do. What is that code? It's really only one, that's the single parity check code. How do I encode? I take my s bits of the message and I compute their sum, C, and that's my overall parity, and my code word would consist of those S and C. Okay? Now, why does it have property P2? That's very easy. So no matter which bit of the message I want, there have to be 2 disjoint recovery sets for it. What are these 2 disjoint sets? Well, I have the bit xi in my code word as is. Okay, so it's part of the message, it appears in the code word. And then if I add all the other bits, so this is addition modulo 2. So if this is true, then the blue one is true. So I add all the other bits except xi. Because their sum is 0, then the sum of all the other bits except xi is also xi. All right? And so my 2 disjoint recovery sets for I are just I itself, and then all the others. Okay, this is clear. So there are 2, they're disjoint, and I can do it for every bit. And I was able to do it by adding only 1 bit of redundancy. Very, very simple. Okay? Now, what I want to tell you is that this trivial observation, based on what we did in the first part of the talk, we can also already state a very strong theory. And here it is. So we basically can do what we promised to. Okay? So what it says is, you tell me you take epsilon s small as you want, and then I can produce a private information retrieval protocol which has storage overhead like this, 1 plus epsilon over n, and communication complexity, which is sort of sublinear. Well, what's the proper name for something like that? No? You don't? Subpolynomial. Okay. Okay, how is this proved? Very, very easy. So you give me epsilon. I'll just take S to be 1 over epsilon. And then I take that. So what will be my storage overhead if S is 1 over epsilon? Okay, it's going to be exactly this. Okay, because I add just one more bit of information, of redundancy. And for the protocol that I'm emulating, I'll take the Vardy, okay, which is the best protocol, best communication complexity known, and it works with 2 servers. Is this clear? So, okay, back to our problem. We're done. So, this is what we kind of said. Is it possible? In fact, we were able to accomplish it. Okay? So we can guarantee full information threaded privacy. We can do that with communication complexity, essentially the best known today, and yeah, and we can do this without doubling the number of bits. In fact, the storage overhead approaches that. Okay, so a good question to ask is, well, okay, so maybe that's it. Why do we need to worry about anything else? And let me give you 2 answers. Okay. So the first answer is something I already mentioned. So if you look at the results of Vardy and before that the results of Vardy and Efremenko, then in fact this is what I showed you before. And Vardy you can get there with 2 servers, but if you allow more servers, then the communication complexity in fact becomes smaller and smaller. And as the number of servers grows large, it approaches something like this. Now, what is that function? It's the log of n to some constant c power. So it's sort of, in a very crude approximation, it's like log of n. Now, to my mind, that's pretty amazing because if you didn't want any privacy at all, if you just want to tell the server, okay, I want item I in the database, give it to me, I'm telling you what I is, how many bits do you need to communicate I? Well, again, n items, and you want 1 of them. What that says is that if you use only polynomially many as much bits, you could do it with full privacy. So where the servers learn absolutely nothing about what that is. Okay? All right, so I do want to get there as far as communication complexity, and for that, I need to consider dealing with larger values of k than just 2. With 2 servers, all I can get is this. Okay, that's one answer. Here's the other answer. So this coding theory problem that we have just defined and solved it for k equal 2, that was obviously the optimal solution. And so the problem was very, very easy, almost trivial, becomes far from trivial and actually very, very interesting if you consider values of k greater than 3. And it has lots of connections that we have discovered. We've been working on this for a couple of years to many, many different things in coding theory, in combinatorics, in graph theory, in other branches of theoretical computer science and whatnot. Okay? So what I'd like to do really most of the time in the second part is to talk about this problem and show you connections, if there's time enough, to these 4. Okay, so Steiner systems and T-designs, majority logic codable codes, bipartite graphs, and constant. Okay? And from each of these domains, we'll take something and we'll use it to construct our k-server PIR codes and get better and better values for the 2 functions that we have. Okay? Now, before we do that, though, let me show you sort of a from-scratch solution that will serve as our benchmark. This is basically generalizing this single parity check code that was the optimal solution for k equal 2 to k equal 3. Okay? So what am I going to do? I'm going to arrange the message bits of x in a square. And previously I just computed a single parity, the sum of all of them, and appended it. Well, now I have a square. I'm going to compute a parity for each row and a parity for each column. And that will be mine. All right? Now, how many of you have seen product codes in coding? How many of you have not seen advanced stuff? Okay, well, the majority still say. Anyway, this is essentially a product code with one difference. In the product code, you also have that bit. Here we don't need to have. Okay, so. Now, why does it work? It's also quite easy to see. So all right, so suppose consider a generic xij. Now we want to solve it for k equal 3. So we need k disjoint, 3 disjoint recovery equations for it. What are they? Well, I have this thing itself. And then if I take all of these bits except xij, then their sum will be exactly xij. Again, the sum of all of these in this column is 0. So if I take xij out, add all the rest, they're equal to xij. Okay? Now I can do the same thing using the parity in the row. And these three, the green one, the blue one, and the red one, they are disjoint. Take xij out, it's over recovery 7. Okay, is this clear? So that's one solution for k equal 3. Now, once you realize that, you say, oh, okay, what can I do for k equal 4? What would you do, having seen that, for k equal 4? Cube, there, yes, cube. And yeah, of course you can do it. And do the same thing. And k equal 5, hypercube, a 4-dimensional cube, you can do it for anything, right? And okay, and if you do that, so all right, so more generally, we arrange that. So we assume the number of message bits in that form. It's not a very limited assumption. And we arrange them in the form of k minus 1 dimensional cube. So notice for k equal 3, you need a cube of dimension 2, because you also have the bit itself as one of the recovery equations. Then you could do it, and you can therefore say, all right, so what's, okay, so for k equal 3, what is my, my overall length? I have the s bits here, and I have a square root of s here, and a square root of s here. Okay? So I have s, in this case 3, 2 times square root of s. Okay? And when k is 3, that is exactly this formula. From k to 3 here, this will give you s plus 2 times square root of s. And for larger values of k, it works. Make the calculation. You can use the calculation. Okay, so with just that, what is it that I can do? Well, I could make the previous theorem. So this is the theorem here that we have seen on the previous slide. This one, I could make it stronger. So this one, so really to prove that, I only use k equal 2, and I just sort of convinced you that it would be much nicer to have larger values of k. Well, now I can restate essentially that result, but for all fixed k, right? So I can construct, so I can take now a k server PIR particle, whatever the complexity it is, will become smaller with larger k, and I can emulate that, no matter what k is, with this storage order. Okay? And all right, now why is that true? All I have to do to prove this is to show that m over s, that ratio will tend to 1 as s grows, or I need to show that rho over s will go to 0 as s grows. Okay? And indeed, this is true. K is a constant, and here I have s to the power, so I have here s to the power k minus 2 divided by k minus 1 and divided by s. And we'll look at this as s grows. Well, that is 0. Because this is strictly less than 1, and this is 1. This does go to 0, albeit very, very slowly. Okay, when k is large, it merges to 0 slowly. Okay, so now what we can do in what follows in this presentation is to make these two, or let's see the redundancy, let's focus on that, approach 0 much faster than what we have. Okay, so we'll have much better constructions of K0. Okay, and the first construction that I want to show is construction from a type of codes that were studied a lot in coding theory. These are known as majority logic decodable codes. And I want to ask you whether you have heard about majority logic decodable codes, because maybe with the exception of Pascal here, I would assume none of you have. They are now completely forgotten. But all right, actually let's learn about it. So what is a majority logic decodable code? It's just a binary linear code of length m, and we say it is a majority logic decodable with parameter j if the following is true. Okay, so for any code word position I, if I look in the dual code, I can find such a set of code words. What are they? They all have 1 in position I, but all the other positions there is 0. So I want to have these are said to be orthogonal on position I. Strange terminology, but anyway, that's the definition of majority logic decodable codes. Now, why were they studied back in the 60s and 70s? Because if you have such a code, then it can be very easily decoded by majority logic. That's where the name comes from, majority logic decodable. So let's learn how that works, okay? So suppose I have a code word, binary linear code, transmit some code word C, and these positions of the code word go through some channel, let's say a binary symmetric channel, and I get the channel out Y. And let's suppose all I want to know is, was there an error in position I or not? Of course, that'll do it for a while. How can I determine this? Well, look, so suppose there was no error. Okay, so yi is ci. In fact, let's suppose we have just ci, no errors at all. And let's suppose we have ci. And we try, so what is this? Each one of these is a code word in the dual code. So you can think of it as a parity check on C, a very basic linear code. Okay? So if I evaluate this parity check on the original code word, what will it evaluate to? 0. That's the definition of a linear code. All the parity checks evaluate to 0. So if I were to evaluate the J parity checks on C, they would all evaluate to 0. Okay, now let's introduce error. Suppose there is no error at position I, but maybe T other errors somewhere else. Well, each of these T errors, because these are disjoint, each of the T errors will affect at most one of the J parity checks. Okay? And J minus T of them will still evaluate 0. Is this clear? Okay. Now suppose there was an error in position I. And again, suppose there are no other errors at this point. Then if I were to evaluate these J checks, they will all evaluate to 1, because in that position, there was an error and no others. Okay, so they will all catch that error because they all have 1 in that position. But now suppose there are T other errors again. This will affect at most T of the checks now in the other direction. Okay, so maybe T of them will now switch back to 0 in the worst case. But at least J minus T will remain at 1. Again, because the other supports being disjoint, an error can affect it. Right, so all I can do is just, so for each position I, any position I, evaluate these checks. If T is less than J over 2, where does it say so? Material encoding. Okay, it doesn't say so. Yeah, so basically, the assumption here is T is at most J over 2 or less than J over 2. Then the majority of the checks will evaluate to 1 if and only if there's an error. Is this clear? So these codes were very, very simple to decode, and as such were extensively studied. You don't need any algebraic decoding. It's very, very easy. You just shift the code word, evaluate these checks, and so on. And then computers became stronger, and we could do algebraic decoding very efficiently, and there's no reason anymore to really study such code. Okay? All right, so now what's the connection between these codes and our problem? Well, I claim it's almost the same thing. So here, so this little lemma establishes a bridge between our K-server PIR codes and majority logic decodable codes. It says if you have a majority logic decodable code with parameter J, it is automatically a K-server PIR code with K equal to J plus 1. Okay? Why is this? Let's take a systematic generator matrix for our majority logic decodable code. All right, so what is the systematic matrix? And you can get it for any code. It's just the one which has the identity matrix in the first K positions. And so E sub I appears in position I in the matrix. So I need K disjoint sets of columns that add up to E sub I. Well, here's one. Here's the first one. It's E sub I itself. Okay? Now I also have, because it's majority logic decodable code, these parity checks. So let's look at this check. What does it say? It says that every code word, if I add these positions, I'll get a 0. So that means for every row in this matrix, if I add, every row is a code word. So every row in this matrix, if I add these positions, I get a 0. So the sum of these columns from here to here is 0. And therefore, the sum of these ones is exactly E sub I. This one is E sub I. And that is true for all the other checks. Okay? And therefore, these are my disjoint recovery sets for E sub I. They're just given to me by the orthogonal, by those parity checks individually. Right? And I have one more than J because I have E sub I. Okay? Good. All right, so now what it means is we can open the books, go back to papers that were written in the 70s. There's a lot of work that went into majority logic decodable codes, lots of beautiful algebraic constructions. This is probably the strongest one. I'm not going to explain it in any detail. There's a book by Lin and Costello on coding theory. Shulin is the author of that paper. There's a whole chapter which summarizes majority logic decodable codes. And combining that theorem with the lemma up there, what we get is this result. So Okay, so basically whenever K is of a special form, that form needs to be like this. Okay, it's one more, oh no, it's two more than a power of 2. Because J is one more, and K is J plus 1. So whenever K is 2 more than a power of 2, then I combine all of that, and I get this. So the redundancy for these values of K as n becomes large is only square root of s, which is much better than this. Okay, so this I have reduced to s to 1. Okay, so for large K, this is much better than K minus 2 divided by 2. Okay? All right, and it's also nice because it sort of revives or makes connections to a topic in coding theory that I've long forgotten. So if you write a thesis and then nobody reads it for 20 years, do not despair, it may in fact become useful again later. Okay, now here's, let's switch gears now. Here's a completely different construction of these K-server PIR codes that will lead us to Steiner systems and graph theory and constant codes. Okay? So to do that, I need a definition. Okay, well, let me do a tricky question. How many of you have not seen a linear hypergraph? Nobody raises their hand. Okay, just sit and good. All right. So what is there is really, I could just say what I need is a linear hypergraph. Let me define it. I'll give it a different name. Okay, so what I want is to have a collection of sets. In fact, I want R sets. They're all subsets of the set of integers from 1 to s, with the following two properties. And they're exactly the properties of K uniform, or K minus, well, yeah, K uniform linear hypergraph. But anyway, so the properties are like this. I want it to be a K cover of the set S, that is subset of. What does that mean? If I take any element of S, it appears in at least K of these. Any I from S appears in at least K of these sets, and I say it's a K cover. Okay? The other property is, well, they can be disjoint, but I can allow a bit of overlap. I want them to be what I call almost disjoint. What does it mean? That if I take any two sets, either they're disjoint, or if they overlap in at most one element. Okay, so if these two properties are satisfied, then this is a K uniform linear hypergraph. Okay, I'll call it whatever, almost disjoint K cover. Okay, now why am I interested in that? Because now suppose you found such a thing, such a collection of sets. I can now use it to construct a K-server PIR code as follows. How do I do that? Again, it will be a systematic code. So the first S positions will be the message itself. And then I'll add R PRDs, one for each of these R sets. And what are they? They're exactly the sums. So here's a A1. A1 is a subset of S. So to get C1, I'll just add the corresponding bits. And I'll do it for each of these sets in the collection, and I get R pairs. Right? This will be my code. Okay, I just specified the encoding. And I claim that this is, in fact, a K-server PIR code. In fact, I gain one more. So it's enough to take a K-1 cover of S and construct a code like this. The parameters are going to be S plus R. That's clear. I just added R parities. And this will be, if this is a K-1 cover, this is a K-server PIR. Okay? Why this is true, let's prove it like this. So, okay, what do I need to prove that this is a K-server PIR code? Well, you give me I. For every such I need to give you k disjoint recovery sets, okay? So here, you give me I will find, this is a k minus 1 cover. So I can find k minus 1 of these subsets that will contain I. Okay, that's by definition. All right, so let's just say these are the first k minus 1. Now let's define A prime by taking I out of each of these k minus 1 subsets. Now these A primes now are disjoint. Why? Because my original ones were almost disjoint. If they intersected in at most one element, but that's I, and I just took it out. Okay? So, all right, so then here are my disjoint recovery equation. I have xi itself, and then if I do this, so what was C1? C1 was the sum of the message bits over A1. And what is A1? That's just A1 prime and I. So this must hold. Is this clear? These are the recoveries. Okay, good. So what I just showed is that if I have such an almost disjoint K cover, it immediately gives me a K-server PR code, and we spent an hour in the morning to show that if I have a K-server PR code, I have this wonderful PIR scheme with low storage overhead. So now this is here. So great. So good. So by the way, my redundancy. So once I use this construction, the redundancy is clear, right? So it's just R. S plus R is the length, S is the dimension. Okay, so where do I get such disjoint, almost disjoint K covers? Okay, and turns out that, well, there's lots of different objects, combinatorial objects, studied in various areas of discrete mass that you could use to produce such disjoint, almost disjoint K covers. So here's the first of them, Steiner systems. All right, so how many of you have not seen a Steiner system? Some people, all right, you were scared by my previous question. I think some of you have, some of you have not, but in any case, let's define it. So what is a Steiner system? So here's an example. So you have some set. In this case, the set consists of 7 elements. They're called points. And a Steiner system is just a set of subsets. They're called blocks, subsets of the original set with the following properties. So this is a Steiner system of strengths 2, QR. So what are the parameters? All of them have size Q. So each of this, so here Q is 3. Okay, each of these subsets has size 3. R is the number of elements, so that's 7 in this case. The property is that if I take 2 elements, that's this 2 here, 2 points, there is one and only one of these 7 subsets that contains these 2 points. Okay, so anyone, say, give me 2 points.
1 and 5.
1 and 5. Okay, let's look. 1 and 5. 1, 1, 1, 1. 5. This one. Okay, this one contains 1 and 5, and there's only 1. By the way, the Steiner systems, those of you that have seen Steiner systems, do you recognize that particular one? Aha, right. So maybe now some of you, thank you, Pascal. So it's one of the most beautiful structures in all of discrete mass. Leads to projected geometries, designs, and whatnot. So, and did they mention this? Did they mention planoplanes at the ISIT?
Yeah. By the way, you know that connection?
Yes, it's the father of that. Good. Anyway, so this is a graphical depiction of the same thing. All right. So now, how would we use Steiner systems to get almost disjoint K covers Well, that's very, very easy. So yeah, so take a look at these blocks. So I'm just going to use the blocks as my subsets in my almost disjoint K cover. I claim that any two of these, if they intersect in exactly one point. They could not intersect in 2 points. Why not? Because for those 2 points, there would now be 2 blocks that contain them. And by the definition of a Steiner system, there's one and only one. Okay? So I can use the blocks of the Steiner system as my almost disjoint K cover. And Steiner systems are known. I could plug in the parameters, and I get what I get. I mean, I get a bound again on the redundancy. So we did that with my students some time ago, and they were quite happy about it, but it's actually quite disappointing. There is something called Fisher inequality in design theory, which says the number of blocks in any Steiner system has to be at least as large as the number of points. In fact, here you see an extreme example. The number of points is 7, and the number of blocks is also 7. Okay, it's called the symmetric Steiner system. In general, the number of blocks would be large, and the number of points would be much smaller than that. What does it mean? So each of them is a set. So and each set contributes 1. So the redundancy is the number of sets. Remember that. So and the dimension is the number of points, S. So what I get, my redundancy is at least as large as the dimension. Okay, so that's not good, because if I get this, what would I get? What is my storage overhead that I can get? The best 2. No, it's 2. So I want rho sk. So I want as shown here, I want rho sk or anything k over s. I want this to go to 0 as quickly as I can, but that bound tells me that rho sk is greater or equal to s, so that ratio is at best 1. Okay, so very disappointing. And so what does it mean? When Steiner systems are just not of no use for us. That's what we thought, except they are, and they actually provide an optimal solution to this problem. All we have to do is to turn them around. Okay, so what are we doing here? Now, so I removed this. Let's look at this. So now, so strange. So as our sets all right, so the points will become the sets. And what used to be sets will become the points. Okay, that works very well. So what I claim is, so here, so now for each point V, okay, so these are the points, let A sub V be the blocks that contain that point. All right, and so now we could say, consider that set of blocks, and I claim that it is almost disjoint. Why is that? Because if indeed, so let's look at A sub 1. And I claim, so the corresponding subset would be 1, 3, and 4. And this is almost disjoint with any other point, because again, if I had an intersection, this would violate the Steiner system. Okay? So what it does now, so Steiner systems in that picture that I'm showing here, they look like this. So now it's like that. So R is here, S is here. Previously was mislabeled, was S here and R here, which was that. Now it's the other way around, which we turn it to R. And now it's a good solution. So it's called, in fact, there's a name of something like this in combinatorics. It's called the dual of a set system. That's what it is. It is not a Steiner system anymore, but nevertheless, it's the dual of a static system. And we can use an important theorem in design theory due to Wilson, 70s again, and we get that. And this is better than what we had before. We get that the redundancy behaves as the square root of S, and now this is true for all values of k. No matter what k is, this works, whereas majority logic decodable codes gave us only certain, sparse values. Okay, so here's another construction of disjoint k covers. This one comes from bipartite graphs. Now, again, how many of you have not? I assume that all of you have seen bipartite graphs. And what I claim is that I take such a bipartite graph. So let me make a drawing. So here is the two sets will be U and V. And I'll take, I'll make that S, so there's S points here. And the subsets of S, so will be the neighborhoods of the points. So I'll call this set is A1, and maybe the other one is A2. So whatever that is. And so I take the neighborhoods, so look at one side, let's call it V. I take S vertices on side U, and there's going to be R of them here, so U will be of size S, and V will be of size R. And I take these neighborhoods, and for each neighborhood, that's a subset of S. Okay? Is clear what I'm doing? So then I claim if the graph has no 4 cycles, then these neighborhoods are almost disjoint, which is why. Why is that true? Because if they are, so suppose there are 2 neighborhoods, so it's still almost disjoint. But suppose there are 2 neighborhoods that are not almost disjoint. So let's draw another edge here. Okay, so now these 2 points, this one and this one, belong to this neighborhood and to this neighborhood. Is clear? Well, that's a 4 cycle because I can go like this, and here I can go here and close a 4 cycle. As soon as I get 2 points in an intersection of 2 neighborhoods, I immediately get a 4 cycle. And so if the graph does not have 4 cycles, then no 2 neighborhoods could intersect in more than 1 point. And that's exactly what I mean. That's the almost disjoint point. Okay, so that's the proof over here, which I just drew. And so now, okay, so what do we need now? So again, the number of vertices on one side is S. That is our parameter. What is K? What is the cover? So the cover is, so I look at U, and I look at the degree. So this point here now is covered twice. The degree of that point is how many times it is contained in some neighborhood. Okay, so to get a large K cover, I need a large degree on the U side. So in particular, to get a K-1 cover, I need that the minimum degree on the U side is K-1. Is clear? And as I just said, I want girth. So what is girth? It's the you look at the shortest cycle in the graph, and the number of edges in it is called the girth. So in a bipartite graph, you kind of easily see any cycle will have an even number of edges. So I don't want to have a cycle of length 4. I cannot have a cycle of length 5 because it's bipartite. So the girth of the bipartite graph that I need is at least 6. These are the kind of graphs that I want. And okay, that's it. So if you give me such a bipartite graph, the number of vertices on that side is S. The degree on that side is at least k minus 1. The girth is at least 6. Then the number of vertices on the other side. So I want the smallest number of vertices on the V side subject to these conditions. So did people actually study this problem in graph theory? Yes, they did. These are called bipartite cages. Pretty esoteric. But, okay, there's some work. And we could now, based on what I just told you, take these results and the cages, and we basically rediscover the square root. Okay, so the same, so standard systems give us, so this is true for all k, but maybe not for all s. And so for standard systems, we get certain values of s. Well, and this is asymptotic in s. In fact, we care about specific values of s and k. So these constructions are not identical. They compete each other. Okay, but asymptotically, they both look like that, squared away. Okay. Oh, and this is a comment. So there's something known as batch codes. Or I'm not going to explain what it is. And for this, you need larger bursts. Okay. How much time do I have?
Sure, but we have some slack for lunch. How much do we need?
Maybe 2 minutes, maybe less. Yeah. So this is the last topic that I want to cover. So we've seen. So we started with a problem that we have just defined from PIR, K-server PIR codes. We have seen so far connections to majority logic decoding, to Steiner systems, and to bipartite graphs. And these are completely, you wouldn't think there's any sort of very different things. Okay? So the last one I want to show is a connection to constant weight binary codes. So what is that? So what is a code, binary code, of length n and distance v, just a set of vectors, binary vectors of length n, and any two of them, they differ in at least 8 positions. Now, a constant weight means that also exactly W is of the positions are 1 in every vector. Okay, that's constant weight. The Hamming weight is 1. Okay? And again, what we want is the largest number of code words in such a code, given W and D and N. And okay, so now let's restrict these parameters. What if we require that the distance, to any two vectors is at least twice the weight? There's only one way in which the vectors could satisfy this restriction, right? So we only have W1s in one code word, W1s in the other, and these supports have to be disjoint, completely disjoint, if we want distance to W, right? Okay, what if I take distance to be 2W minus 2 in such a code? So we'll look at those parameters. I claim that this will happen if and only if the supports of the code words are almost disjoint. So if they intersect in exactly one position. Okay, it's clear? This is how I might get my disjoint K covers. All right, so this is the number of vectors, S. This is the number N. Well, again, what I could do now, I could take, somewhat trick what we do. I take all the code words in the constant wave code, and I'll use their supports as covers. So in this way, I will get an almost disjoint K cover, except really, again, I need to take the dual system of them. I need to now look at columns in this matrix rather than rows. Okay, and we still satisfy the same property. And anyway, so, okay, based on that, I could say that the redundancy is the smallest n such that the number, so I need to set up my parameters properly, the number of code words in a constant weight binary code of length n with distance 2k minus 4 and weight k minus 1. This will guarantee the k minus 1 cover, and this being twice that minus 2 will guarantee that they're almost disjoint. So such a thing has to be greater than s, and it's the smallest n itself. So again, now I could go, and there's has been work in coding theory on constant wave codes for decades, and I could go to known results and look up tables with these parameters and asymptotic constructions. And if I do that, I again, in general, recover asymptotic units. Okay? So at this point, you might suspect that this expression, square root of s, there's something specific, something special about it. I use 3 different constructions and different ways, and I still get the same answer. And indeed, that is the optimal. So we have a bound in the upper direction now, and that's the best we can get. But I will present it here. So took us a year and so to prove it. It's not easy.
What's the constant?
We don't know, actually. So the constant depends on k, right? So k is the parameter is how many sets you need. And we know, in fact, this is optimal. For k equal 3, this turns out to be the optimal solution. And we also know the answer for k equal 4, but it's open for k equal 5 and all right, so that leads me to this table. So now what we did, so how did we generate this table? So we took all of these constructions and more, and we compiled the best results from each of them, and we also have a bunch of propagation rules. Like you could say, oh, if for this s in this k it is 30, then here it is at most 31, something like that. There's a bunch of rules like that. We ran a computer program, and this is the best. And as I already mentioned in answer to Pascal, we know, so this is S, this is K. We know that in these codes, well, 2 is just 1. That's the trivial solution. That's the single-parity check. That's redundancy. We know that these 2 columns are optimal. In fact, we could continue them to infinity. We know exactly the formula for k equal 3 and 4. But as of 5, it is open. And it is an interesting research problem. And I'd be happy if any one of you, so the slides are posted, so you can take any number and build something that improves upon this number. We want to make them as small as possible. Okay, so we don't know the answer for K5 and above, and it's a research problem to improve any entry in the state. Okay, now this is the same table, but now converted into storage overhead. So as I have seen, so this table here is in terms of row S and K, and what is the storage overhead? We've seen this at the beginning of the second part. Storage overhead will simply 1 plus Rho Sk over S. So, okay, so given rho S and K, I could compute the storage overhead, and this is what that table shows. And what I'd like to emphasize is, all right, so what do we see here in the first row? That's the storage overhead we get with one server. That's the conventional PIO. And now if we go to 24 servers, so not asymptotic, it's still quite a 24 servers. You know, any number in this table is what I would consider a reasonable number of servers. So we can already get from, you know, you can see the reduction. So for example, here, from storage overhead of 16, we get down to a storage overhead of about 4, and you can check it out. All right, that's the end of my talk. So, yeah, if questions or more questions.
Questions from the audience?
Yeah. Yes.
Can you outline the idea behind the proof of the
Which upper
So
bound?
you said that they would be bounded.
Oh, goodness. Right. So, in fact, there are two different proofs. And neither of them is easy. So I guess, yeah, maybe I'll just tell you the key idea, which is kind of surprising. So we start with, let's take an identity. So this is the matrix G of the K-server PIR code, and let's label these columns, let's call them V1 through VR. Surprisingly, it looks that we, to prove the bound, we need to consider that set. Vi times Vj for all ij. Now, how do you multiply two binary vectors just component-wise? That's a strange operation that seldom shows up in coding theory. So considering the KPIR constraint, looking at the set of such products and giving a bound on the dimension. So if they have that constraint, the set of all such must have a large dimension, and from there the bound.
Other questions?
You talked about what majority logic being equal. So what you talked about was one step.
Yes.
There are two step and so on.
Right.
Is this useful?
No, actually. So yeah, right. So people don't know about majority logic decoding, and the name is already quite long. Majority logic decodable codes. I should have called them one-step majority logic decodable codes, but I skipped it. Yes, no, we cannot use the two-step ones. We don't know how to. It would be nice to. I mean, that's one of the research problems I suggested to my students. Like if you have a multi-step, could you still get something out of that? We don't know how to do it. Because there are many more constructions. Right? Yeah, there's a paper of read molecules presented in a minute by Vijay Kumar and students that sort of does that.
I had a question. So these are, I mean, this is a very coding theoretic problem, right? So you want perfect reconstruction, no probability of error. You want no information leakage whatsoever. Is there, does a information theoretic version of the question even make sense? Would the bound behave fundamentally differently? like small information leakage, small property reconstruction error.
Right, so turns out, so people actually looked at that, and they, along those lines that you suggested, they couldn't really, I'm not aware of any work. Let's put it this way, there is a line of work which does use information theoretic tools and gets nice results. It's mostly by CGFR. But this one modifies the model in the following sense. We have assumed throughout that the number of bits in every item is just one. Every item is a single bit. They say, oh, well, every item is a file, is a record, and let's make the size of that go to. And then they talk about capacity, that limit, and things like that, so it becomes better. So in fact, one good problem is to combine their work with ours, and that hasn't been done. Yes?
Just following up on that question, so is there any, do we get any benefit if we go to higher
Good question, actually. So I mean, you could consider the database to start with, or all instructions. In other words, the linear combinations are not just binary additions. We did look at it a little bit, but not a lot. So I would think there would be benefit. So we could get better instructions, better rates, but we haven't really studied that.
So perhaps in the interest of everyone's empty stomachs, we can take questions over lunch. Professor Vardy will be joining us, right? And will be around generally for part of the rest of the week, right?
Right. I should be around at least today and tomorrow, so I'd be happy to answer any questions that you might have.
My pleasure to assume there for the speaker.
Thank you. Thank you very much.
So student helpers should be able to help you go towards the lunch menu. So if you head up to the 9th floor, there should be people waiting up there.